This is a Perceptron in C++. I utilize the Glute graphics library to visualize learning that the Perceptron undergoes. This file is a tester file. It includes the actual Perceptron here, which is this file. The Perceptron is this object with properties weights and learning rate. The Perceptron will determine coefficients of an equation, and using that equation can make a decision with new data. So the data that we provided is a vector of 500 points. Each point has two features, an x and a y. Two features, it's easy to visualize two features, so that's why I'm using that. And when we supply the Perceptron with the data, it needs to be guided. It needs to be provided examples on what exactly is a correct decision. So along with the dataset and the two features, we provide the correct answer, which is this variable upper label. And then we assign a color to distinguish the two decisions. And as this process is happening, we can classify the data with a line called the decision boundary. So this is an instance of a class line, and a line is just 2 points, x, y, and x, y. So as this process begins, we initialize every point with two features randomly between 0 and 20. If they add up to at least 8, we'll label a decision yes with a 1 and assign a color. Otherwise, we assign a decision no with -1 and a different color. And we've stored those points. And with the setup, the decision boundary, so the equation that the Perceptron is working with is this. So it's just as we assign the values, it's greater than, they add up to greater than or equal to 8, it's a yes. If it's less than 8, it's a no. So the decision boundary uses this equation to determine the second variable, the y. So we supply it with the first dimension, -1 and 9. These are values just outside the data set. Totally arbitrary. So this is for the graphics. I won't go into too much detail. This is about the Perceptron. So the graphics starts a loop, and everything happens within the loop. So the loop, in a nutshell, happens here, and it's a double buffer. The graphics involves double buffering. So it clears one buffer, it draws to the buffer and does miscellaneous things, and then swaps the buffer. So as one buffer is written to the screen, the other buffer is being written, and then swap. So we draw the scale. So this is 2 dimensions, 2 features, just easy to visualize on a mathematical Euclidean space diagram. So we draw a horizontal and vertical scale, and we draw all the points, and then we're going to draw wherever the decision boundary is. It's going to be different places, but these will always be the same. So it's going to draw the decision boundary, and then the Perceptron's going to do its work here, and it's going to go loop around. So when this is where the Perceptron work happens. So let's follow this. So the train here, for each data point, we're going to get its features, send it into this, and then we're going to send it to Perceptron here with the correct answer. So as we jump over here, it's going to be sent to its own train function. Just a point before that begins is when the Perceptron is created, we give it assign it a learning rate, and we assign random weights. 2 weights. It has to be working with 2 features, so we're going to have 2 weights. We have a weight for each feature. So we send the features of 1 point through here, and we're going to guess what the Perceptron is going to make a guess with those features and what the correct decision should be. So it comes in here. We're going to add the first feature of the first data point times the first weight of the perceptron plus the second feature of the data point times the second weight of the perceptron. Add those together and then throw it into this other function, sine. If there are at least 8, it's going to guess a yes or a 1. Otherwise, a no with a negative 1. Now we could well, there's a bias, so there's x times w0 plus y times w1 it's greater than or equal to 8 or less than 8, or we could just use the bias. That's called the bias, and then we can set it, we could greater than equal to 0 or less than 0. But I placed the 8 on the other side where the 0 was, and that's why it's like that. So going back, we had the perceptron make it a guess, and after the guess, that value, that positive negative value is sent in here. If the guess matches with the actual, then we're not going to do anything. We're just going to return a value 1. And that's for tallying. Tally the progress. So let's return 1 here. It's going to add up for every point, or add up. If they add up to all of them are correct, if they guessed all of them correct, those weights should be good. So they can have the perceptron make future decisions now. And this is a bit of a progress report. However many of 500 are correct is the percentage complete. So going back here, if it didn't make the correct guess, it'll just change the weights, and it'll keep changing until it's correctly classified all the data. Now I looped this after all 500 points have been looked at and guessed at. So the visualization is a little bit smoother than if we've flashed to the screen after every single point. So I suppose with a visualize after every point, it'd be a little more sporadic. However, I haven't done it, but that's what I suppose. But here's what I have. So this is the decision boundary here. The green dots below are no, or -1, and these pinkish dots are +1 for yes. And as you can see, it's still making incorrect decisions. And it's complete. It's found these weights. It's correctly classified all 500. So if we give it a new point, say x1 will be 4 and x2 will be 8. It brings it up here. You plug those values into this equation and it will be greater than 8. Now let's run it again. Let's see the variety. As that's going, I'm going to change the learning rate here for the next time, and we'll see how much quicker it goes. Sometimes one end will actually go back and make incorrect guesses for what it already made correct guesses for, but it'll take times to redo points anyway. I compiled this with these flags I found necessary for the glute library to work. So there's a bit quicker there. You can see it shifting around a little sporadically. And it's done. And that will complete the presentation.